All right, welcome to Physics Teacher. What I'm going to go over in my live session today is, well, my grade 11 physics class will be having their first unit test on kinematics in 2 days. And I thought it's probably similar for a lot of other students in Ontario or elsewhere, whoever finds this useful, is I'm going to go over a review for our kinematics unit test. Specifically, the concepts I'm going to go over is some problems involving motion graphs. I'm also going to go over our 5 equations for uniform accelerations, and we'll do some problems with those. And then finally, I'll go over a problem for projectile motion. If you have any questions, you can let me know in the chat. I'll either get to them now during the review, or if not, I will create videos later addressing some of the questions if there's a lot of consensus for that. All right, so let's start with motion graphs. So here's the first problem. Here it says, sketch a velocity time graph from the data, label the axis, and include a title for the graph. I think my face is covering up some of that. Let me see if I can fix that, make this a bit smaller. There we go. All right, so here we have some data. Now this is time and this is speed, and it looks like initially we go up 0, 12, 24, so we're increasing speed at a constant rate, and then our speed gets maintained at 48 meters per second. So to draw our graph, and as a teacher, I will take off marks if you do not label your axes. Lots of students lose marks because they don't label their axes. So our vertical axis is our velocity. Include your units, meters per second, and include your direction. Okay, notice this says they're traveling east. So we're going to put our direction in square brackets. Right? Now, because we're increasing at a fairly steady rate, I'm going to draw an increasing slope starting at the origin all the way up to a speed of 48. So this will be the point right here. So we have 0.4 and 48. And then we maintain a constant velocity from then on, where this will be our last point, 0.7 and 48. All right, so there is our velocity time graph. And let's look at what the next question will be. Here it says sketch an acceleration time graph from the data. Again, label the axes. Oh, I forgot to label the axis. Time in seconds. I just lost marks on my own test. All right, label the axis and include a title. All right, so before we can start doing that, we have to look at the slope. If you want to know the acceleration from a VT time graph, you have to find the slope. So we're going to find the slope here. Over here, this is a horizontal line, so we know that the slope is going to equal 0. So to find the slope here, we're going to use these coordinates. We'll use 0, 0 because that's an easy one to work with, and we'll use this coordinate here. So we'll write slope, and that's just rise over run. So we have 48 minus 0, that's our rise, all divided by run, 0.4 minus 0. So that gives us 120 meters per second squared. All right, so if we want to draw a acceleration time graph with this one, I will put it down here because it's not very complicated. We will have our time in seconds, and over here our acceleration in meters per second squared east. So initially we have a value of 120. So we'll label that here, 120, and then a value of 0. So there is our acceleration time graph. All right, so let's move on to our last question. It says, using the velocity time graph, determine the displacement of the object after 0.7 seconds have passed. So let me just erase some of this here. So to find the displacement from a velocity time graph, what we need to do is we need to find the area under that graph. So you can look at this sort of sideways and calculate the area of a trapezoid, but what we'll just do is look at it straight on, and we'll calculate two areas. This one we'll call the area of a triangle, A1, and this one the area of a rectangle, A2. So the displacement will be the sum of those areas. Right, so area 1 for a triangle is just a half base times height, where our base is from here to here, which is 0.4, times our height, which is 48. And we get an area 1 of, let's grab a calculator, so 0.2 times 48, 9.6. And that's in meters. Then we calculate area 2. That's just a rectangle, so it's length times width. Our length goes from here, from 0.4 to here, 0.7, which is a total length of 0.3. 0.3 times our height, which is again 48. 0.3 times 48, 14.4. So if we add those together, we get a total displacement of 24 meters. Don't forget our direction, east. All right, so there's an example of motion graphs. Make sure you know to go from a VT graph to an AT graph, you're finding the slope. To go backwards from a VT graph to a DT graph, you're finding the area under. Similarly, if your teacher asked you to find the velocity from a position time graph, that would be the slope. Okay. All right, so let's move on. We're going to try some other questions now. Now we're going to do two questions of examples where we'll have to use our 5 equations of uniform acceleration. So let's try this first one. Here we have a basketball player jumps vertically upwards to a height of, here we go, to a height of 1.6 meters. What was his initial velocity? Now students usually find this confusing because I usually say, I don't have enough information. They only tell me the height. Well, let's go over it. Okay, that's the height. So if we have a basketball player jumps up, my wonderful art skills here, up 1.6 meters, what is that actually telling us? Yes, it's height, but it's also, from the point of view of our equations of motion, it's telling us our displacement. So our displacement is 1.6 meters up. And I usually like to make up our positive direction. So let's just have that as a positive value. Now, because we're doing this on Earth, there is another piece of information we know. We know that the acceleration is 9.81 meters per second squared. And because it's down and I've labeled up to be positive, that will be negative. So now we have 2 pieces of information. Now the third piece of information you need to remember is when you jump up, once you reach that maximum height you get to, before you start coming down, anytime you change direction, at that instant your velocity is going to be 0. So we're going to write our final velocity for that max height to be 0. So now we have 3 pieces of information. And anytime you have 3 pieces of information, you can solve for the other 2 using our 5 equations of uniform acceleration. But since it wants to know initial velocity, we really don't care about time. So we're going to use the equation that does not include our time variable, which is this one, Vf squared equals Vi squared plus 2a delta d, where this whole term right here is going to be 0. So then we can bring one term to the other side, rearrange to sort of isolate for Vi. We get negative 2a delta d. And then take the square root of both sides. So Vi is going to equal the square root of -2. Don't worry about the negative because a is also going to be negative, so that's going to cancel. 9.81 meters per second squared times our displacement, which is positive 1.6 meters. And when we do that, we get a velocity, an initial velocity of 5.6 meters per second. How's everyone doing? All right, no questions? All right, let's try another problem then. How about this one? Here we have a skier slid down a very icy hill with an acceleration. So they're giving us acceleration. Let's write that down. It's important to show your work. And one of the ways we show our work is by writing all of our given information. So 2.44 meters per second squared. And the direction is just going to be down the hill. Right? So we'll just leave that out. For 18 seconds, so we know time. It's going to be 18 seconds. If she started from rest, so that's telling us initial velocity as 0 meters per second. How far did she travel? How far means we want to know displacement. All right, so in this one, we don't care about final velocity. So our equation then is the one without final velocity, which is VI delta T plus 1/2 A delta T squared. Okay, and VI is 0, so this whole term, because 0 multiplied by whatever time is just going to be 0, disappears. So we're left with delta D equals 1/2 A delta T squared. Make sure you've practiced a lot so you're really good at rearranging equations, because it can be frustrating when you know the physics and you understand the physics, but you can't get full marks because you can't rearrange the equations. So make sure you become very proficient at rearranging equations. But in this case, we're solving for delta D, so it's actually quite easy. There's nothing to rearrange for. It's already isolated. Just 1/2 A, so 2.44 meters per second squared, times time, which is 18 seconds, and squared. So we get a displacement of 395 meters, and the direction would just be down the hill. Okay? So last thing is going to be the longest question, the one students have the most trouble with, projectile motion. And I've got this into 3 parts so we can analyze it in different ways, but we should always start a projectile motion question by drawing it out and writing down our given. So here we have a football punter kicks a football with a velocity of 30 meters per second, an angle of 45 degrees. That's a good angle to kick at because that is the angle to give you maximum range. But it's also important to note that a football field is flat. I mean, if it was angled, one team has a serious advantage over the other, so it's flat. That's a pretty reasonable assumption we can make. Our initial velocity is going to be 30 meters per second, so we're just drawing this out. And it's going to undergo a sort of parabolic path here. Something like that. All right, and then something we should do is also, since we know our angle, we should split that initial velocity into a horizontal and a vertical component, or an x and a y component, a Vx and a Viy. The reason why I don't put initial on the x component is because in projectile motion, grade 11, we ignore air resistance, so there is no acceleration occurring in the x component, and therefore that x velocity will never change. So we don't need an initial and final variables for those. But for y, we do, because of, well, gravity. So how do I calculate those? So it is a right angled triangle, so we're going to use our trig ratios. We can calculate the x by using cos, so the cos of 45 degrees is equal to adjacent, which is Vx, over hypotenuse, which is our 30 meters per second. Okay, we can multiply by 30 to get Vx equals 30 cos 45. Or if you know your special angles, 1 over root 2, I think it was. But as a decimal, we have 21.2 meters per second. Now you could do the whole thing and do sine of 45 equals VIY, but because it's 45, sine of 45 is equal to cos of 45. So we're actually going to get VIY to be the exact same thing, 21.2. If you can find symmetries in projectile motion questions, you could really reduce the amount of work you have to do to solve it. All right, now I want to put all of our given information, this is what I usually tell my grade 11s to do, is to make a chart where we write everything we know in our x component and everything we know in our y component. So in x, we now know what Vx is. It's 21.2. But that's it. We don't know our range or our displacement in x, and we don't know the time. In y, we know our initial velocity in y. Again, it's 21.2. Just leave out my units because I've run out of space. We know acceleration. And acceleration I'm going to make negative because I'm going to use this typical coordinate system of positive x and positive y. So acceleration will be negative 9.81. Again, meters per second squared. Just run out of room. And I'm going to leave it there. Let's go on now and try to solve for part A. So part A says determine the horizontal and vertical. Oh, I did that already. We're going to move on to part B. So part B is calculate the time of flight of the football. I did part A without even noticing it because you should always start your projectile motion questions by drawing a picture, writing down your givens, solving for your components, right, before you even need to really look at what the question's asking. All right, so time of flight. We have two options. We can either look through our x components and use equations to solve those, or our y. Now in x, we only have one equation because there's no acceleration. The only equation is displacement equals velocity times time. That's it. And since I have two unknowns there, there's nothing I can do here. But in y, I have two pieces of information, but I also have a third, because this is the time of flight, how long it's in the Air Force. Let's say it goes from this point A. Let's call the peak B. We'll need that for part C of our question. And when it hits the ground, C. So it's going all the way from A to C. Now, if you imagine that on, say, a coordinate plane, then this is perfectly horizontal. Your y component or your y coordinate would not change. So your displacement in y for this situation is actually 0. And that's our third piece of information that we actually need to know in order to find the time. So now that we have 3 pieces of information, when you're dealing with your 5 equations of uniform motion, as long as you have 3 pieces of information, you can solve for the other 2. And we've got 3. We want to know time. So we are left with the equation that does not include final velocity. Let me just make some room because I'm going to run out of space and get rid of part A here. All right, so the equation that we want to use, this equation you see the most often in projectile questions, is this one. So VIY times time plus 1/2 A times time squared. Now it looks like a quadratic, and it is a quadratic, but luckily we won't need our quadratic formula because one of these 3 terms is 0. And then we can divide every term by time. The only reason why we're allowed to divide every term by time is because we know, without a doubt, time will not be 0, because you don't want to make that math error of dividing by 0. But time can't be 0. It's the time of flight of the ball. It's a positive value. It's not 0. So here, time will cancel. Here, time cancels with one of them. And we're just left with 0 equals VIY plus 1/2 A delta t. All right, so let's bring 1 over, and we'll make it negative. So we have 1/2 A delta t is equal to negative VIY. Then we can multiply by 2 and divide by A to get time equals minus 2 VIY divided by A. So VIY we know is 21.2 meters per second. Again, don't worry about that negative because it's about to disappear, because acceleration is minus 9.81 meters per second squared, which gives us a time of flight of about 4.3 seconds. There's our time of flight done. All right, let's move on to part C. Just erase some of this here. These questions require a lot of space. All right. So part C, we have to calculate two things. One is the range, and one is the height. The range is fairly simple. It's delta dx. And since I now know that time, which is what I just erased, but I remember 4.3 seconds, I can now use our equation in our x components to solve for that. There's only one equation. One equation you can ever use in x, since there's no acceleration, is this one right here. I don't even need to rearrange it. We have our velocity in x, 21.2 meters per second, and our time, 4.3 seconds. So we get a range of 91.2 meters. Okay, that's easy. Now the last one, to find the height, you have two methods that you can do this. One, because this is nicely symmetrical, you can take the total time and really just sort of split the problem in half and say the time to maximum height is half of 4.3 seconds. And then using that time, figure out what that vertical displacement is during that half time. Another way you can do this, and the way that I prefer to do it, instead of using a value I just calculated and rounded to only 2 significant digits, what I'm going to do here is I'm going to realize that at the peak, its vertical velocity in y will be 0. So now I'm going to go back and use, this is the initial condition, this is the acceleration, and this is the final condition. How far did it travel? So using these 3 pieces of information, we can go back to our equations of motion, use the one that does not have time, and figure out what that maximum height is. So we're using this equation. Vfy squared equals Viy squared plus 2a delta dy, where that delta dy is now going to be our height because we're using those 3 conditions. Okay, so this term is 0. Now we're just rearranging. Bring one term to the other side. So we have 2a delta d is equal to negative Viy squared. And then divide by 2a. Let's move over here. So we have delta d, or our maximum height, is going to be minus Viy squared all over 2a. So plug in what we know. So minus, so Vi is 21.2 meters per second squared all over 2 times negative 9.81 meters per second squared. And we get, let's write it over here, 22.9 meters. All right, I hope that was helpful. I don't see any questions in the chat, but if you have any further questions, you can access this later without it being live. Ask me questions in the comments and I will do my best to address them either in the comments, or if it's a long question, maybe I'll make a separate video for that. Good luck on your tests and have a great March break.